Hi everyone, greetings of the day. This is Dr. B. Ravi Chandra. In the last lecture, we have studied about the design of FIR filter using Fourier series method, and we have seen the process of how the process is going to take place to design the FIR filter using Fourier series method. So in that scenario, we came across some disadvantages that is happened in the design of FIR filter using Fourier series method. So in that process, one phenomenon is occurred which is nothing but Gibbs phenomenon, where when we are truncating the signal into FIR, there some Gibbs phenomenon is affected. So that Gibbs phenomenon is overcome or reduced by using some windowing techniques. That means multiplying the desired frequency response with the windowing techniques, that Gibbs phenomenon will be reduced. So in that scenario, let we discuss what is meant by windowing methods in this particular lecture. So that is how these linear phase FIR filters are used using the windowing techniques, how these linear phase FIR filters are going to design. So in that in this lecture, let me see what is windowing technique in digital filters, why we are going with the windowing techniques, and what are the types of windowing techniques, and finally we will see some steps how these windowing techniques are used to design these FIR filters. So let us start with what is meant by windowing technique. So if you see here, when we consider a discrete time signal h of n, consider the discrete time signal h of n, consider the discrete time signal h of n. I'm considering here the discrete time signal h of n that contains infinite number of samples. So that contains infinite number of samples. So here I am considering the discrete time signal which is h of n, which contains the infinite number of samples. So now our goal is to extract a finite number of samples. Why? Because we are discussing about design of FIR filter. No? So that's why I want to convert this infinite number of samples into finite number of samples. Our goal is to extract the finite number of samples which is present in the discrete time signals h of n. That means here I have taken the h of n which is having the infinite number of samples, and our goal is to extract this h of n into h dash of n, which is nothing but which contains some finite number of samples from it. So here, after obtaining this h dash of n, this results a new signal. So h dash of n is nothing but a new signal h dash of n. That is, here what happened? We have achieved this conversion of infinite number of samples into finite number of samples, and this can be achieved by using a technique known as windowing technique. Okay, I think you got the point. That is, our agenda is to convert h of n. What is this h of n? This is a discrete time signals, and it contains infinite number of samples. It contains infinite number of samples, and our goal is to convert this h of n into h dash of n. What is this h dash of n? It is nothing but it is a discrete time signals which contains finite number of samples. So our goal is to achieve infinite to finite number of samples. So how it is going to happen? It is going to happen with the help of a technique which is known as windowing technique. So what is meant by windowing technique means? The windowing technique is nothing but this technique is used to convert all the infinite number of samples into finite number of samples. So for this, what is h of n? H of n is a original infinite number of samples, and h dash of n is nothing but the resultant new signal, and this resultant new signal is nothing but finite length signal, finite number of sample signals. Okay, so this is nothing but the windowing technique. So how this achievement can be happen, how this conversion can be happen means, let me take one simple example. Now taking the windowing technique as placing a window over the input signals. For example, you can observe this particular diagram. I have taken one big screen. Which is nothing but, see here, I have taken one big screen. In this, I am placing one window. So I have big screen, and this is nothing but the window, which is nothing but window. So now the input signal h of n is passed through the screen. The input signal is passed through the screen. So what happens? Here, this screen will allows only a particular samples, and it restricts the rest of the samples. See here, this window allows only a specific number of samples to pass through, the specific number of samples to pass through while it restrict the rest of the samples. So these another samples will be restricted at the outside. So the output which is formed through the window is nothing but h dash of n, which is a finite length of the signal. Just we will take one small example. Consider one simple window which it is covered with a mesh, and if air is flown hardly through from outside through this window, this mesh, what it will do, it will restrict all the dust particles to enter into the house. It allows only the air, purified air. So all the dust particles will be filtered with the help of this mesh, and only the air will be allowed. So that will be a good example, so that here this window, what it is going to do, it allows only the finite number of samples to pass through that window, and rest of the samples will be blocked at this screen side. So like this, we are going to filter the infinite number of samples h of n, and it is passing through the window, and only the pure, that is the finite samples will be passed through the windows, and that finite samples is nothing but the h dash of n. I think it is clear. So live example, we can take the window which is covered with a mesh, so that the dust particle, that is the restricted samples will be stay through the mesh, and it will be filtered, and the remaining air will be go to the inside, will pass through inside the room. So that purified air we can call it as a h dash of n, which is a finite number of samples. Okay, so this is nothing but windowing technique. What it is saying, this window allows only a specific number of samples to pass through, while the rest will be blocked here. The rest will be blocked here. Okay, the output which is formed at other side is nothing but h dash of n, and what it is a finite length signal. So mathematically, how this process is represented. So we can show this as mathematical representation. See here, to form a windowing mathematically, so what we have obtained at the output side, we obtained h dash of n, which is a finite length signal. How it is obtaining? When the infinite number of samples, that is h of n, when it is passed through the window w of n, getting my point, when h of n, which is infinite number of samples, when it is multiplied with the windowing technique. So when it is passed through the windowing technique, this infinite will be converted into a finite number of samples, so that the h dash of n is obtained. So this is the mathematical representation, how we are going to obtain the finite length sequence, by multiplying the infinite length sequence h of n with the windowing function, so that I can obtain the h dash of n. So we can just for more clarity, let me take another example. Consider 4 samples. I want to get only 4 samples when I multiply this h of n with the windowing function w of n. So how it is formed, let me see with some different types of graphs. So for example, if we want a finite signal with 4 samples, so I want only 4 samples, that is I want only h dash of n should get only 4 samples. So we take the infinite length signal. So we know that we are taking the infinite length signal h of n, and what we are doing, we are multiplying that with the windowing function w of n. So like this, if I do that, what I am going to get, which is designed to allow only 4 samples. Why? Because our agenda is to get only 4 samples, and we will design like that, so that when h of n is multiplied with the windowing, only 4 samples will be passed, so that the output will be 4 samples, that is h dash of n. So for this, I am taking h of n. So h of n is nothing but it is a infinite number of lengths. So you can see all the negative and positive parts, and it is infinite number of samples. This multiplication effectively selects the desired portion of the signal, giving as a finite length of output h dash n. So how it is happening, let me see with this graph. So I am considering h of n, which is a infinite length of sequence, and this h of n is multiplied with a windowing function. So in this scenario, we will come across 2 windowings. One is anti-causal window and second one is causal window. So what is anti-causal window? If we select samples from both negative and positive, okay? If we select the samples from both negative and positive sides, for example, n is equal to 2 to n is equal to plus 2. So minus 2, minus 1, 0, 1, 2, 3. So we got positive samples as well as we got the negative samples. Both sides we got. So if a sequence H of n have both signals, that is positive signals and negative signals, then that signals is said to be a anti-causal or anti-causal window, and it will be rarely used in the windowing technique. So this is one of the anti-causal window. And what is causal window? If we select only the starting point, that is from n is equal to 0 to n is equal to 3, only non-negative terms or only positive terms if I am considering, then that type of window is said to be a causal window. See here, if we select samples starting from n is equal to 0, 1, 2, 3, so on, only positive sides. So all being non-negative, it is called as a causal window. So these causal windows are widely used in real world application. So why we are recalling these two windowing means, we are multiplying h of n with causal windows. See here, how do we select 4 samples using windowing means? To extract 4 samples, our agenda is to extract the 4 samples. So from infinite signal h of n, we define a windowing function. Which windowing function I am defining? I am defining only causal windowing function. You can see here, only non-negative terms, non-negative sequences are obtained at this particular graph, and we can call it as a causal window. Okay, so see here, W of n is equal to 1 for the desired 4 samples, and rest of the other samples will be equal to 0. So W of n is equal to 1 for resulting samples. I need only 4 samples. That's why I'm 0, 1, 2, 3. So I need only 4 samples. For these 4 samples, I will have the value all ones. Rest of the values will be equal to 0. Okay. So like this, windowing function, which windowing function we are taking? We are taking the causal windowing function, and how it should be? It should be W of n is equal to 1 for the desired 4 samples. I need only 4 samples, and our agenda is to take only 4 samples at the output side. So that's why W of n is equal to 1 from 0 to 3. That is 0 to 3 means 4 samples, and rest of the samples will be 0. So this is the two conditions. So we got h of n, which we have seen in the first graph, and now we got the causal function, causal window, which is nothing but W of n. And the final thing is nothing but what we have to do, we need to multiply this both causal window and h of n, causal window and h of n, so that we are going to get the h dash of n. See here, only the required samples is h of n. So here see, sorry, this is the causal window. This is the causal window. This is nothing but this is total h of n infinite length sequence. Now only the required samples, how many samples we want to get? We want to get only 4 samples, 0, 1, 2, 3, 4. So for that, what we are going to do, we are taking h of n, which is containing both negative terms as well as for positive terms, and if I am multiplying this with the windowing technique, which is nothing but causal window, if I multiply, what happens here? You can see here, since 1 into value is equal to value, so whatever the one value it is multiplied here, that values only I will get. So if I get 1 into 0, 1 into 1, 1 into 2, 1 into 3, so like that, only the values which is present when it is equal to 1, that value is only present, and remaining values, what is remaining values? All values is equal to 0. That's why no values will be obtained. So that's what here we can see, only the required samples in h of n, the required samples in h of n are passed. How it will be passed? Because of this window, in window we have set from 0 to 3. So this is the window. So if I pass this h of n through the window, only these samples will be multiplied with the h of n, that is 0, 1, 2, 3 values will be multiplied. Why? Because this values is equal to 1. So when 1 into this h of n value is equal to, I am going to get that values, h dash of n, and remaining values what it here? I got only 0. So 0 into any sequences in h of n will become 0. So what I am going to obtain? If I pass these through the window, only the windowing values which is equal to 1 will be multiplied with h of n, that values will be present in the h dash of n. So effectively, all other samples are blocked. So why? Because it is equal to 0. All other samples are 0 in the windowing. That 0 will be multiplied with the h of n. That values will also become 0. Like that, effectively a window of width. How much width this is? 4. A window of width is opened. We have set like that. A window of width 4 is opened, so that only 4 sequences will be passed through this window, so that I am going to get h dash of n with 4 samples. So you got a clarity how we are going to get the infinite, how we are going to convert the infinite length sequence into finite length sequence. Here we are given the infinite length sequence. After multiplying this sequence with windowing, how many samples I am going to get? I am going to get only 4 samples. Like that, I have prepared one window with a width 4, which is opened on the signal. This acts like a screen. This acts like a screen that permits only selected samples. How many samples I have selected here? I have selected only 4 samples. That samples will be selected and it will pass that samples through the window, and this is the samples which is selected at the windowing. So like this, we are going to convert this infinite into finite. That means our agenda here, how many samples? 4 samples. From infinite to 4 samples we have converted with the help of a windowing technique. This is the process how we are going to use, how we are using this windowing technique for the conversion of the infinite signal sequence to now infinite sample sequences. Fine. Now, why this windowing technique is used? I already told you, because of presence of the Gibbs phenomenon in the Fourier series method. We will recall, to reduce the Gibbs phenomenon, the Fourier series coefficients of the filters are modified. How it is going to reduce this Gibbs phenomenon? It is reduced by multiplying the infinite impulse response. Multiplying the infinite impulse response, that is nothing but, what is that impulse response? That is hd of n with a finite weighting sequence w of n. So hd of n into w of n. So this process is said to be a windowing technique. So why this multiplication is done? To reduce this Gibbs phenomenon which is present in the Fourier series method. So this is the mathematical representation of the window, that is w of n is equal to, or w of minus n is equal to 1 when up to mod n less than or equal to n minus 1 by 2, otherwise it will be equal to 0. So this is the windowing function. This windowing function is going to multiply with hd of n, so that I am going to get h of n. Let's see. After multiplying the windowing sequence w of n with hd of n, I am going to get a finite duration sequence. See here, I am going to get finite duration sequence h of n that satisfies the desired magnitude response mod n less than or equal to n minus 1 by 2. So this is the simple mathematical representation of windowing technique, how this windowing technique is going to multiply with desired impulse response to get the finite impulse response h of n. So with the help of this windowing, we are going to reduce the Gibbs phenomenon which is present in the Fourier series method. So based on these windowing techniques, there are different types of functions. So here, these are different types of functions which we can use any type of windowing technique to multiply with the desired impulse response hd of n. The first one is rectangular window, second one is triangular or Bartlett window, third one is Hanning window, fourth one Hamming window, and fifth one is Blackman window. So these are the different types of windowing techniques how we are going to use to convert that infinite length sequence into finite length sequence. Let me see what are the conditions that that is given for this each and every windowing technique. For the first thing, rectangular window, and the condition for this is WR of n. WR of n. So which is nothing but the rectangular window. It will be equal to 1 when mod n less than or equal to n minus 1 by 2. At that magnitude, the value of the rectangular window will be equal to 1, otherwise it will be equal to 0. Be careful, you have to keep this in mind. It is very important while you are going to solve the problems. These conditions are very useful, and without knowing these particular conditions, you cannot able to solve the problems in the upcoming lectures. So please keep it in mind. What are the conditions we are studying? Please keep it in mind that first one, rectangular window, WR of n is equal to 1 when mod n less than or equal to n minus 1 by 2. And you can see here how the representation of this rectangular window. When the window is 0 less than or equal to n less than or equal to 7. From 0 to 7, it will be equal to 1. You can see all the values equal to 1, and it represents the rectangular window. So it represents the rectangular window. Sharp edges in time domain. high side lobes in frequency domain. So this is first one, and the condition is WR of n is equal to 1, mod n less than or equal to n minus 1 by 2. The second one, the triangle or Bartlett window, and the condition for this is WT of n. WT of n is equal to 1 minus 2 mod n minus 1. That is, WT of n is equal to, it will be 1 minus 2 mod n by n minus 1 within the condition, that is mod n less than or equal to n minus 1 by 2. Otherwise, it will be equal to 0. So this is the condition for the triangular window, or else we can call it as a Bartlett window. See here, the triangle representation. You can see it is in the form of a triangular shape. And very important, it is a linear tapers to 0, better frequency characters when compared with the rectangular, which we have seen in the previous slide. So this is the condition for the triangular window, and it is also one of the technique to use for the design of linear FIR filter. The next one, Hanning window. The condition WH of n. WH of n is equal to 0.5 minus 0.5 cos 2 pi n by n minus 1. So it is 0.5 minus 0.5 cos 2 pi n by n minus 1, and this value will be from mod n less than or equal to n minus 1 by 2. Okay, so this is nothing but the Hanning window, and it will be like some bell shape. It will be like some bell shape. Okay, it starts from 0, smooth bell shaped curve, lower side lobes than triangle. So when compared with the triangular, the previous side, the lower side lobes, the side lobes are very lower when compared with the triangular, symmetric bell shaped window, and the condition is that. So this is another windowing technique. Next one, Hanning window. So for this, I am indicating with Wm of n, which is equal to 0.54 minus 0.46 cos 2 pi n minus 1 from mod n less than or equal to n minus 1 by 2. And if you see here, when we compare this Hanning window with Hanning window, here it starts from 0.08 and somewhat like this. Where Hanning window it starts from 0, but here it will be starts from 0.08, and it is also resembles like a flat top symmetric window. Okay, and the condition is 0.54 minus 0.46 cos 2 pi n minus by n minus 1. And the final thing, Blackman window, which it resembles, the condition is WB of n is equal to 0.42 minus 0.45 cos 2 pi n by n minus 1 plus 0.08 cos 4 pi n by n minus 1 for the condition mod n less than or equal to n minus 1 by 2. So these are all the 5 important techniques, windowing techniques, which is used to design the linear phase FIR filter. And finally, let me see how we are going to design this FIR using different techniques. The process will be same. At one scenario, the changes will occur by using the different types of window. Let me see. First, what we are going to do, we will find the desired impulse response HD of n. In the first step, we are going to design the desired impulse response. After giving some specifications in the problem, by using the specifications, in the first step, we will design the HD of n. After determining this infinite length impulse response HD of n, in the second step, we are going to use the windowing function. Okay. After getting the HD of n, the second step, we want to find out the windowing function, that is W of n. That windowing function may be anything. What we have studied, the five types of windowing. 5 types of windowing we can use here. So depending upon the problem what they have asked, we can use Hanning, Blackman, rectangular, and rectangular window. So any one of the windowing function we can use in the second step. So after finding this W of n, our agenda is to compute the coefficients. After getting all the windowing function coefficients, and finally we are going to multiply this desired function with HD of n. Here we will get some coefficients of all HD of n. These HD of n coefficients will be multiplied with the coefficients which is occurred in the W of n, which is windowing coefficients. After getting all the total coefficients, we are going to multiply that HD of n and W of n to get the h of n. Okay, so here the third step we are going to find out the value of h of n, which is the multiplication of first step and second step coefficients. What is first step? Desired impulse response hd of n. In the second step we are going to find out the windowing coefficients in the second step. So after getting these two coefficients, in the third steps we are multiplying the two coefficients hd of n into w of n, finding the value of the impulse response h of n. And finally the transfer function will be formed here. See here, obtain the transfer function h of z by taking the z transform. Whatever the equation we are getting here, this will be z transform and will be converted into h of z. So what is that equation? Summation n is equal to 0 to n minus 1. We are doing the h transform, z transform for the h of n into z power minus n. So this is the equation to find out the value of h of z. And finally we are going to get the frequency response by substituting all z is equal to e power j omega. We are going to get the final equation, which is nothing but h of e power j omega is equal to summation n is equal to 0 to n minus 1 h of n e power minus j omega n, which is the finalized equation with the final coefficient. After getting this, we can able to draw the diagram by using some different types of forms like direct form, one direct form, to cascade or parallel form, which we have studied in the previous slides. So this is the 5 important steps to design the FIR filter using some different types of windowing techniques. So I think you got a clarity what are the steps. First step hd of n, second step w of n, third step h of n, that is nothing but multiplication of first step into second step hd of n into w of n. After getting h of n, we are going to convert that into z transform, and the equation is h of z is equal to summation n is equal to 0 to n minus 1 h of n z power minus 1. After getting this, just substituting the value of z is equal to e power j omega, this h of z will be converted into finalized equation, which is nothing but h of e power j omega, that is equal to summation n is equal to 0 to n minus 1 h of n e power minus j omega. So these are the important 5 steps to design this particular FIR filter using some different types of windowing techniques. So in the next class, we will use all these 5 different types of techniques one by one, and we will take one problem for each techniques, and we will see how it is going to design the FIR filter by using that 5 steps, which is rectangular, Hamming, Hanning, triangular and Blackman window. Thank you.